Hello. Hi guys, good morning. Welcome back to the new video. So basically, no matter what, if you have solved it, if you have intuition, no matter what, just to solve this problem. It is the first problem we have seen so far, like up till last 2 months, we have been doing the problems daily. It is the first problem we have seen on DP plus bitmasking. I told you, but still, that is what we want to see. So for sure, stick to the end. Maybe you can skip the parts too where you see, okay, I know this part, I know the bit masking part, I know this part, all that stuff, but still, I highly recommend for the new folks especially, just watch this video. And for sure, it is 7:53 right now. It took a time to actually make this whole stuff, and that's the reason my 8 o'clock contest will get missed, but still, maybe it will take half an hour or so to actually record it. After that, I will give the contest. So yeah, live stream will for sure come. Cool. Starting with this problem, it says that maximum score after n operations. Now what it says is you are having a number, nums, an array of positive integers of size 2 into n. My words, of size 2 into n, which means if the n is, let's say, whatsoever, here you can see the n limit is 7, so the size of the array, it can go to 14. For sure, cool. You must perform n operations in total. If the size of this array is 2 into n, I have to perform n operations in total. And what that one operation look like? The ith operation. When I say ith, it means first operation, not the 0th operation. It starts from 1, 2, 3 up till n operations. So basically I say first operation, second operation, third operation, nth operation. That is how I tell it. Cool. Choose two elements x and y. Choose two elements x and y. Basically we have this array. We have this array called as nums. We have this array called as nums. So now we choose two numbers x and y. We receive the score, which means after choosing these two numbers, the score I have got is I into GCD of that number x and y. I is nothing but the operation, which means if it is the first operation, I will have I as 1. If it is the second operation, I will have I as 2. Now remove x and y from nums. Okay, x and y are just removed from nums. Now they are no more in my nums, which means in the next operation, I can't choose them at all. Return the maximum score you can achieve after performing n operations, which means at every operation I have to choose two numbers, and then the next operation I have to choose next two numbers, again next two numbers. So basically I have to find such order of sequence that I at every operation choose two numbers, and then this score part. Basically I am concerned about the score because as I choose x and y, it will just get multiplied by the operation number, which is 1. That is the reason. Okay, x and y is nothing but the GCD when I say. So operation wise, it will be next is 2 into those two pairs, 3 into those two pairs, and so on and so forth. So basically I have to, at every step, I have to choose two numbers, add in my score, next choose two numbers again which are not chosen so far, and then make my score. Let's look at, okay, we got the question, what it is saying. Let's look at the example to actually go on in brief that, okay, some greedy part or anything is not applied or something is happening here. Then if you have only numbers 2, 1 and 2, for sure in one operation I will just choose the two numbers, which is 1 and 2. I will get the answer as 1. But the operation has 1 into GCD of 1 and 2. That is pretty much it, which means at every operation I choose two numbers. I just do, if it is operation 1, then okay, 1 into GCD of those two numbers x and y. In the first operation, in this example, I choose number 3 and 6. Next operation I choose 4 and 8. Next operation I just had these 4 elements. Answer is 11. It is the maximum possible score I could achieve. If I would have chosen this 4 and 8 in the first operation and this 3 and 6 in the next operation, then it would have been 2 into GCD of 3 and 6. It would have been 1 into GCD of 4 and 8. That would have been less. That is the reason I have to optimally choose. Okay, basically I have to start with some pair. Then after that I have to go on to next pair, because here it could have been any case. Maybe I started from 3,6. What if I started from 3,4? What if I started from 3,8? What if I started from 4,8? I have many options to start from, right? Like many options I can go to start from. But the optimal one was actually when I choose starting as 3,6. Next operation, I just choose 4,8 because 3,6 was already chosen. So I can't choose those two. In the last example, the best optimal score I can get is 14. And how? In the first operation I just choose 1 and 5. Okay, 1 and 5 are gone. Now I can choose the next operation as 2 and 4. Okay, then 2 and 4 are also gone. Right, next operation, like the operation last, which is operation 3, I can choose 3 and 6. By this order I can just get the maximum result. Now one thing I got so far, okay, I cannot choose any number. Yeah, for sure I just know I'll choose the minimum pair GCD for the one operation, which means 1 into some value which is minimum, then 2 into value which is like bigger than that, which means the GCD pair is low, then higher, but still how to choose that GCD pair itself, which means which GCD pair I choose now, that later on it would not affect my answer. So it is very much dependent upon, okay, what should I choose now that my later answer is not affected. So it is not one thing. Okay, I can't greedily just choose, okay, let's just choose these two pairs and for sure it will have this answer, which means I have to try every possibility. When we say every possibility, it means that, okay, if I have these numbers, now the numbers are 6, so I will represent my numbers, which means my nums array having all the numbers as m. So m is 6, but the operations required are actually n, which is like nothing but m by 2, which is 3, because operations are for pairs and pairs will be nothing but m by 2. So the operations required which I have to do is 3 operations on this. Now at the first operation I can choose, see I have this array nums with me. At the first operation I can actually choose to like a pair. To choose a pair I have how many options? I have m square options, which means with a1 I can have a2, with a1 I can have a3, with a1 I can have a4, with a1 I can have a5, with a1 I can have a6, with and so on and so forth. And same I start for a2, then a3, then a4, and then a5, and then a6, and so on and so forth. So basically to choose the first pair itself I have m square operations. But before moving on to this thing, let's quickly have a look at the constraints. The constraints are pretty small, n up till 7. So for sure, the first thing should come in your mind is let's try brute force, which means let's try all the possibilities out, maybe, because I could not think of anything greedy as such. So for sure one thing comes in my mind, okay, the constraints are very less. For sure some brute force thing, which means exhausting all the values, considering all the values would be the case. So I'm just having the same thing. I'm considering all this stuff right now, which means for to choose the first pair, I will try all the m square possibility of pairs, which means a1, a2, and so on and so forth. So basically, I will have m square pairs with me to choose from. But for simplicity and not to clutter the our window of explaining, I just choose let's say 2 pairs. But I'm again saying they will be m square pairs, but I choose 2 only for you, which means let's say at one example of I just choose a1 and a3 as one pair, and let's example one operation is a2 and a4 as one pair. Now first pair I just choose, and again I'm saying it can have many other pairs also, like a1, a5, a1, like many m square pairs it can have. So I'm not drawing all the m square pairs, I just had this arrow which shows okay many pairs are actually possible. Now when we saw this, okay, one pair is chosen. When we choose a pair, we add that score in it. So it was the first operation, thus operation value is 1. Now the GCD I will add for a1 and a3. Cool. Here if I just choose a2 and a4 as a pair, then operation is nothing but 1, same, but the GCD value will be for a2 and a4. Cool. Now as I choose this first pair, again the possibilities will open, which means to choose the next pair itself, again I will have m minus 2 square options, because remaining elements are nothing but m minus 2. So again to choose, now for this, okay, first pair is I have chosen, but for this first pair itself, when it is being chosen, to choose the next pair itself, again the number of elements remaining are m minus 2. So nothing but it is m minus 2 ka whole square number of possible pairs it is having possible, like it is possible. So basically for this one pair, next again it will have m minus 2 pairs possible. And let's for now by our simplicity again take just 2 pairs. Just two pairs, just these two pairs, which means A1 and A3 were already chosen in the last step, operation 1. In the new operation, which is operation 2, I just choose A2 and A4, and one option can be I just choose A5 and A6, and other, I'm again saying it can have multiple many of m minus 2 whole square, again options it can have. Now for this, again what I will do is operation into GCD of nothing but A2 plus A4. I will add my existing answer, which is the above answer which I found. Operation is nothing but 2, and it will just go on and compute this stuff. Cool. And again, if I just choose A5 and A6, then for sure same stuff. Here also, when I choose A2 and A4, again the number of remaining elements will be m minus 2 whole square, m minus 2 whole square. Thus I will again have simple to choose from m minus 2 whole square. Let's for simplicity again choose only two pairs. Now I will choose A1 A3 for this, let's say, and A5 A6 for simplicity. Now again it will just go on. Okay, for this number of again pairs remaining are m minus 4 whole square, again m minus 4 whole square, same for this m minus 4 whole square, m minus 4 whole square, and we just keep on repeating like this. But it is a simple recursion we saw. Okay, for the first operation, I just tried to choose all the m square pairs, and then when I choose those pairs, whatever numbers are remaining, then I'm again trying to make pairs out of it and adding in my answer itself. So it's a recursion which we saw, a simple recursion which we saw. But if you just go on and look clearly at one of the case, it is very visible that our recursion is having repeating sub problems, which means here also m minus 4 square pairs would have been remaining, here also m minus 4 square pairs would have been remaining, and again I would have did the same stuff. So won't it be better that if I just compute, okay, if these many pairs are done, just get the answer for that. Okay, so basically I can just have a memoization part. Okay, if this all these pairs, which means here we can see A1 A2 A3 A4, the pairs A1 A2 A3 A4, this part is already considered. So if it is already considered, just get me the answer for it, and I will not compute that stuff again and again, which means I can just have a memoization part. Which means I saw repeating sub problem. I just tried, because see, I knew brute force would work because constraints were low. So I just tried to actually try every possibility out because constraints are very low up till n equal to 7. Then I just saw, okay, it is to try on every possibility is nothing but recursion. Now when I was trying the recursion itself, I just saw, okay, problems are repeating. So basically it has a repeating sub problem part. So it is nothing but dynamic programming. You saw, okay, recursion is there, time programming is there. Now it's just simply implementing that same stuff of recursion and just memoizing that part, and we would be good to go. Now before going on to the implementation of recursion, let's recap what we have to do. So basically a simple recursion which we have to implement, a simple recursion, nothing but we have to choose a pair, because at operation we have to choose a pair, and for sure I can choose in total m square pairs I have. So basically I will have two for loops I, j, which actually bring out those m square pairs. Okay, choose a pair, and as I told, pair can be m square. So okay, choose one pair out of those m square pairs and add its score. Now score was computed by operation. It is okay, first operation, second operation, third operation, and the GCD of those two chosen numbers. Cool. I can find the GCD by myself or by using a standard n-bit library, which is __ GCD, and also in like every language we have this library. So for sure we can just use that. It's a simple GCD function which takes O of log max number time. So okay, that is done for our GCD. But choose a pair and add its score by this value, provided choosing a pair that is already not chosen. So for sure I just wrote my simple what I have to achieve in simple English words, and then I'm just trying to interpret those English words into actual computer science or loops thing, which means I will just try, okay, I have to choose pairs, and I know I can choose m square pairs. Now I can only choose a pair when it is not chosen. So I have to also mark a condition before choosing a pair that, okay, is it already chosen or not? Now to actually mark the condition that, okay, to keep a track of a pair, or basically the numbers which actually I can choose or not, because see, I have these numbers. At a point I can just try, okay, shall I choose this I and j pair? But for that, these I and j pairs should not have been considered yet, which means, let's say if I was trying to make my new stuff as, let's say, a2 and a4, right? a2 and a4. So for sure I can't make a1 or a5, or basically a3 or a5, or basically a3 or a6, because a3 was already chosen, a1 was already chosen. So apart from a1 and a3, others can be considered to make the pairs. So we have to make sure that, okay, I am not considering the numbers existing which can't contribute in pairs, because they have already been considered. Now, to keep the track of the numbers which have been chosen, I can have many ways to keep track. One way is simple to have a vector, which means I can because see, I simply know I have at max 14 numbers. I can place a 14 numbers array. It is actually a hash map itself, right? So it is the reason I have written vector or a hash map. And when I say map, it is unordered map, simple as that, or hash map in Java. But still, it is actually so, okay, I have 14 numbers, and for every number, if it is already counted, I will just store, okay, if it is already counted, I can just say, okay, that location, which means that index, for this reason, if for this thing, I can just say I will have this vector part, vector stuff, and here it will just show me, okay, this is 1 and this is 1, which means A0, A1 and A3 have been considered. Now you can choose other stuff. So I can have this vector or a map which will actually say me, okay, it is considered. So you can choose it, which means you don't have to worry about the number not being chosen. So if the vector is having 1 at that location, at that index, which means that index is already chosen, I can't choose it, so I will not choose it. So basically you will say to update that index is nothing but O of 1, and to see, okay, that index has a value or not, to actually see, okay, that number has been considered in a pair or not, it's also O of 1. But the space will be required for the array itself. The entire array will be used, although the size is small of 14 itself, but still the array is being used, right? Okay, the space will be O of m. Other part we can use same part, like as equal as a map, to check if the number has been considered so far, which means the index has been considered so far. I can use a set. I will just store all the numbers in my set, and I'll just keep on grabbing the numbers. If the number is in my set, okay, it has not been it has been used. If it is not in my set, it has not been used, which means I can use it. I can simply use a O of log n, or basically you can also use an unordered set, as simple as you want. And the space again, because the set is storing all the elements physically with them, so it's just O of m. Also, although I'm saying m is 14 constant, but still it is actually, I'm showing, okay, all the possibilities you have. Last option to actually make the check, okay, the number has actually come or not, which means the index have been actually considered, which means because at every operation I'm just considering my pair I and j. So at this I and j, which means at this next operation, has this I or j been considered so far? We can use a simple mask, and that is how we just see, okay, we just saw recursion happen, we just saw we can have it by DP. Now we just also saw masking is something you actually should know, that it actually is very helpful and very short. Now what this masking will help us do is, I'll just show what is masking live, but it will help us do the part to check, okay, if this number is considered or not, if this number has occurred or not, and to actually, okay, if I consider this number now, which means ith number now, then I can just update this mask in O of 1 time, and I can also see, okay, if this is considered so far or not, by also in O of 1 time. And also the space is nothing but O of 1, because this mask is a simple number itself, which means a simple integer itself. 8, 9, 4, this is a mask. Now as I spoke about mask, and the problem is entirely on this, although you can solve it by these also, I'm not saying you can't, but as the most optimal thing is via mask, because you saw now that it is using the least, and it is the fastest also, because the operations involved are bit operations rather than finding operations in the array itself. So for sure it's much faster you can actually think of with these in comparison. So, and it is for sure we are using DP with this masking stuff. It is the reason the problem is called DP plus bit masking, and it is a very good problem to consider. Now at this point of time, I just have this mask with me. Now let's see, for the folks who know masking and stuff, you can skip this part, but the folks who don't, let's see what is masking. Masking is nothing but a number only, as I showed you above, 4, 5, 6. Now what the masking represent is, if I just say, okay, if the number is A1, A2, A3, A4, A3, A4. Now, if the number, if A1, and let's say, okay, let's imagine as A0, A1, A2, and A3. You can imagine it as like this also, because it is the 0th number, it is the first, the second, it is the third number. Now, if the number is set, which means if the number has been considered, which means the number has occurred, I will put at 1 as I showed. Okay, in the array I can put a 1, okay, to see, okay, if the number is considered or not, 1 if the number is considered or not, 0 if the number is not considered so far. So same, I can just make a array kind of thing to actually show you, okay, it is 1 1 0 0. Now you saw one thing, you also represents the bits in the form of, if I just want to represent my 3, I will represent the same number as 1 1 0 0, right? Basically it is like writing from left to right, and it is writing from right to left. So please don't get confused, it is actually the same stuff which I wrote, because here the indexing starts from 0, here the masking, which means the bit starts, its number starts from right to left. So please don't get confused by this. But yeah, for I can represent the same number by this stuff actually. So basically it is converting that 1 0 0 1 kind of structure in actually to a number, because I actually know I can convert my 1 0 1 0 combination actually back to a number, and that is the reason. Although I made an array to show you, but I can actually convert this particular thing into a number itself. And now, Aryan, that looks nice, that okay, I just have a visited kind of array, then I am just simply using my like bits part, because bits are also 1 and 0, which actually can show me, okay, if the number is visited or not. But how will you check if the number has been visited, and if the number is visiting, you are visiting a number now, then how will you see, okay, let's mark this number as visited? That's a simple operation of bits, that okay, mask is 3, as I showed you, to actually show you that okay, 0th number and the first number have been considered. Now let's imagine that I want to check, okay, has the 0th number been considered? Then I can simply do one thing. I have this mask. If I do a 1 left shift I, which means, okay, left shift 1 is number, okay, left shifting that number by XYZ bits, let's say I bits, it will actually, let's say if I have, I will write A0, A1, A2, A3. Now let's say if I want to check, okay, what is the first? Is the first bit having number set as not? So what I will try to do is, I will try, okay, if I want to check if the second number has the bit as set or not, I will try to make a number something like this, 0 1 0 0, because to check, okay, if only A2 is set or not. If the mask has, because see, for sure, if I do an AND operation right now, then whatsoever result I will get, please don't consider the red part. I'm just using this part because I can't erase it, because it will just get cluttered. But to actually do an AND operation, what you will see is, okay, if this is the, ultimately my aim was to check, okay, if this A2 bit, if this A2 is actually in my, have been considered so far or not. So I just made a mask something like, okay, 1 0 0 0, which means only that bit is 1, rest all are 0. So for sure, if you just do an AND operation with this number, then ultimately, okay, it can be a question mark, but rest all will for sure be 0. Now, the question mark, it can only be 1 when this bit in my mask itself is actually a 1. Only then my actual this question mark, which I showed you right now, it can be a 1, which will actually show me, okay, if this number ultimately mask and my 1 left shift of I, because I want to look for ith number, I equal to 2, which means the second number I want to look. If 1 left shift I, it is this thing, mask, if it is resulting in number which is more than 0, anything number which is not equal to 0 or more than 0, which means the bit was actually present. Else, if it is not present, then it will entirely be 0, which means actually it will be entirely 0. That is the reason how I will check the presence of a bit in my actual mask, that okay, if that number is present or not. So I'll do a simple mask and 1 left shift I, and I can simply get, okay, 1 left shift I for I equal to the 0, which means the 0th number, I'll just do a 1 left shift of 0, which is actually a 1. This bit is set, it will just give me a 1 here, and as it is not a 0, which means okay, my 0th element was actually present in my mask. That is how I will check the existence of a number in my mask. But Aryan, okay, you check the existence, but you also have to update, right? Because if you choose, let's say the number was not present, and if you choose that number, then you have to update your mask. How will you do that? As simple as that. Here I just choose to do an AND operation to actually figure out that bit. Now I know that bit is unset. The mask bit, which was the second bit, was unset. I have to make that bit as set. I have to make that bit as 1. So if you want to make any bit from 0 to 1, you can apply what operations? You can apply either a XOR operation or a OR operation. Simple as that. It is, and I will simply apply an OR operation to actually convert this 0 back to a 1. So by this OR operation, I'm converting that bit, which means if I just choose, okay, simply choose the second element, which means I do a 1 left shift of 2, I'll get a 0, 1, 0, 0, 1 left shift by 0, 0, 1, 0, 0. Then I will just do OR operation, which means this bit which was existingly a 0, it will just become a 1, and that is how I will make my bit as set. And it is all just O of 1 operations, and also these are the bit operations, so it's actually faster than the standard O of 1 operations which you have. That is the reason how you will actually update your numbers. Now simple, writing the code itself is very easy. You will do exactly the same stuff which we showed above, that we will choose a pair, and a pair, which means we have in total m square pairs, and basically add the score by this operation into GCD of a of I comma a of j, and then to choose a score, to choose a pair or not, I just have the below operation of bit masking and stuff to actually figure out, okay, if I can choose that pair or not. Cool, let's quickly see the code. It's pretty easy. Firstly, I just go on and initialize my DP array. Simple memoization step, as I have told you earlier many times. Memoization step, simple. Initialize your DP with your entire size. You will say, okay, Aryan, you took the mask as your DP state. I'll go on to that later, but for now, let's, okay, initialize, okay, you initialize your DP by something. Although it is, you can see it is the mask, which is 2 raised power m. It is a mask, but we will actually go on to it. Maybe we just know, okay, I have to have some DP state, and it's initialized. Calling the recursive function which we have right now with us, as simple as that. I just go on to my m and n, which means I just go on to my m. See, m is nothing but, as I showed you above also, entirely my m, which is nums dot size, and my n is nothing but nums dot size by 2, which is the number of operations. For sure, if the operations have been done so far, which means I have completed all n operations, no matter what, just return a 0. And it is another memoization step. If your DP of mask is not equal to -1, then for sure return the DP of mask, because you actually can see, right, in your DP, in your recursive step, you have your operations and you have your mask. I'll go on to it later that, okay, why operations is not used as a DP state, although we standardly know that, okay, we can have a DP of operation and mask as a DP state, right? Because in recursion, we are actually passing in our operations and mask. And why mask is being passed? Because operation is for sure needed. Okay, I am at first operation, second, third, and fourth, and so on. And why mask was needed? Because actually we know that, okay, what all pairs have been considered so far to actually go on to the next pair itself. Because at let's say operation equal to third, I just need to know what all 4 numbers was considered so far. So for that, my mask will help me. Okay, what all 4 numbers were considered so far. Cool. But you will see that, okay, I'm grabbing only the mask. I'll show that why I did not choose my operation as a DP state, but for sure in recursion you can see I am passing my operation and mask as in the recursive function, but I'm only memoizing mask. For sure, I'll just show you that later, but for sure, let's imagine that, okay, you are actually storing the value of your operation and mask as a DP state itself. For sure, if it is not equal to -1, then return that DP state. Then it will actually just go on to, as I told you, all the m square pairs, which means all the m square pairs, it will just go on and it will just get all the m square pairs. But I can go on to a pair only when that ith bit, which means that ith number is not used, which means mask and 1 left shift I, which means ith number is not used, then only I can go it. If it is used, if it is having some value, then I can continue, go on and try the next number. But if it is not used, then go on and try the j. And for j also, just check, okay, if that jth bit is not used, which means if that jth index or jth element of my nums is not used, if it is used, continue. If it is not, then actually you can go on and make a new mask, because right now you are choosing your numbers ij. You choose your number ij, you just make a new mask by just one left shift I, one left shift j, and as I showed you, you can just do an OR operation and or. You can do an OR operation or a XOR operation, right? So because you just want to make your bit which was 0 as 1. Cool. I can just simply do this stuff to make my bits as set of I and j, and I would be good to go and get the new mask. Now, for sure, I just choose a pair of I and j. For sure, add that score, which means operation, which because I have stored operation state so far, operation I have into GCD of numbers, nums of I and nums of j. It is a standard in-bit library underscore GCD, which you can use, which will actually give you the GCD of that number I and j, and it is the score of that number I and j. But also for sure, I have to again consider much more numbers, because it is only operation is like the operation is OP only is done, right? I have to try for operation plus 1, which means the next operation also, because let's say I've considered only the first operation, I have to try for the second, third, fourth, and so on and so forth. So I just go on for next operation, and the new mask will actually be saying, okay, I have considered my I and j. So basically the new mask is updated by saying I and j have been considered, so please pass the new mask, and ultimately I just get the maximum, because see, for every operation, for the operation 1, I need the maximum score, right? That's the reason for this particular mask, which means let's say only 2 elements were chosen, which means operation 1 was there. So either it can be possible that okay, 0 0, the elements right here, or the elements right here, or the elements right here, anyone can be chosen. So for that I just need, okay, if operation 1 is being chosen, then what is the maximum I can get for that particular operation? That is by my DP of mask. It is nothing but I'm just getting the maximum out of my DP state. Again, I'm just saying that I'll just show you that why this operation and mask. Although my DP state is operation and mask, but I'm only using my mask because it is sufficient. Operation won't be required. It will actually reduce our complexity. But I'll show why it is done. But yeah, for sure you can actually see that okay, you are just wanting every operation to be done, and you just get okay, what is the maximum value out of it, and ultimately standardly return the DP of mask. Now you will see that what we did here was using this operation and mask in my recursive function. So for sure the DP state should have been a operation and mask itself, but my DP state I showed you had only mask. Why, Aryan? Was operation not required? But we saw in the code itself, if it is being passed the argument, which means it is required. But I'll say, hey, operation was required, but the mask itself is storing the inbuilt power of operation, which means if I can just have the mask, by that mask itself I can actually know the number of operations. So basically operations itself by himself will have no significance in the answer, which means if I have the mask as something like this, which will show me these all 4 bits are set, which means all these 4 numbers have been considered. If the 4 numbers have been considered, for sure the operations would have been 2, which means the 2 operations would have been done. That is the reason the mask internally stores the power which operation can do. That is the reason my mask is itself sufficient as a DP state, because it's actually storing the operation power which operation can do. That is the reason I just had my DP of mask itself, because you know, if your DP state would have been an operation into mask, so basically if the complexity, if it had been only mask, then it is the addition of that operation, which means recursive function, it will be nothing but 2 raised power m, but because of this it would have been m into 2 raised power m. That is the reason I have just reduced my DP state. Cool. Let's go on to the complexity of the problem. It's very important. For sure you are having a recursive function where you are actually going on to operations mask, but I actually told you that it is not operations into mask. My operations into mask, only my mask is also sufficient as a DP state. Thus, although earlier it would have gone to operations into mask number of states, but right now because of this mask only, it will just go on to O of mask number of states, my recursive function. And as it goes to every recursive call, it will have a O of m square call to all the pairs. As we saw, at every recursive call, it will have O of m square calls, and at every call of O of m square pairs, to find the GCD, it will have Because see, it's a simple complexity of a GCD, which is log of maximum number which we have out of these both two, and maximum we can see that it can at max go up to 1e6 because num's maximum value can go up to 1e6, so maximum it can go up to 1e6. So in total the complexity will be nothing but mask into O of m square, mask into O of m square into log of m, where m I told okay it is 1e6. Mask is nothing but simply if I have m numbers, so at every number I can choose either a 0 or a 1, 0 or a 1, 0 or a 1, and if we have m numbers, so it is nothing but 2 raised power m. That's it. So mask is nothing but a 2 raised power m into m square into O of log 1e6. Now it is a complexity. Space is for sure mask only because you saw the DP state is also having the mask itself, which is nothing but 2 raised power m. Now can we actually optimize it? Although it's a bit of small optimization, but can we optimize it? Yeah, we can. Because see, it is nothing but the thing which you are doing for all the, because see, it is the thing which you are doing for the m square operation. The GCD you are finding only for these m square numbers, right? So why I am multiplying this by every state? No use. So I can just remove this part, because see, it is together, because for every recursive call I need to have a call to every m square numbers, and it is together that for every m square number I have to call a, okay, what is the GCD of that pair? So both these can be separated out. Thus I can reduce my complexity. How? What I can simply do is, and you will see it is actually fast, but actually I will use a space also, so space got reduced a bit, but yeah, for sure we can actually just compute the GCD of all the m square pairs itself, pre-compute that and store that in my 2D array. GCD of I comma j will store the actual GCD of numbers I and j, and it's nothing but O of m square into log of 1e6, which actually, and for sure the space uses O of m square. Now because of this stuff, what happened is our new time will be this mask into O of m square, which means our number of recursive calls, and for every recursive call I will have m square pairs, but now for m square pairs I will just get the answer in O of 1. How O of 1? By just pre-computation of GCD of those m square pairs. That is how you will get the answer, by just O of m square into O of log. It is the pre-computation part which you did, and for sure and basically it is very small in comparison to what we have right here, so we can ignore this part. We will have mask into O of m square, which is mask is 2 raised power m into m square. That is the final time complexity, which is the most optimal complexity of this problem. Space is again increased. Earlier it is mask only, but m square space for the GCD pre-computation is increased, but for sure again it is small in comparison to mask, so I can ignore that. I will have the mask as the complexity, space is nothing but 2 of m. Code for C++, Java and Python is down below for your reference. That is all. I hope that you guys got the entire intuition of DP with bitmasking. Firstly with recursion, then having the intuition of grabbing all the values, then going on to bitmasking, knowing about the bit operations and all that stuff. I went on to deep specially because of the bit operations, because I want to actually make sure that okay, in future a bitmasking problem comes, then you should be able to solve and apply operations of bits on a number. For sure I will just end the video and I will go and give the contest. It's already 8:30 and contest started at 8. I'm already half an hour late. I will go and give the contest, but yeah, see you in the next one. Goodbye, take care.